Okay, so in last video, I think I stopped at question 3. So here's question 4. So a system can have a equilibrium solution, which is not at an origin. So at the last example, we can see that, like, if you zoom in, you can see that another equilibrium point is at 0, zero point 0.5 and zero point 0.5. So you can read through this, but for part A, we're going to use p-plane to plot a servo orbit to solution B in the xy plane, and then find out that the equilibrium point is about, oh, sorry, and find the approximating linear system of B stars about 0, 0. And we're going to turn in the plot. So I close up my p-plane. So it's going to go ahead and open that up. So for system B, it's going to be x prime equal to x times 1 minus x minus y. Oops. And y prime, we're going to put in 0.75 y minus y squared minus 0.5 xy. And our window, going to change it to 0 and 1. And 0 and 1 for the y as well. So graph the phase plane and plot. Yep, and this is going to be your plot. And another for B star. Yes, so we're gonna plot u and v instead of xy this time. So u prime equal to 0.5 u minus 0.5 v. And v, we're gonna have negative, supposed to be negative as well. So negative 0.25 u minus 0.5 v. So this is from, oops, negative 10 to 10. And plot a few plots. And we also have, oops, okay. So you're gonna find the eigenvalue and eigenvectors in part B. So we're gonna use MATLAB for that. And I already put in the code. And once you run it, you should get the corresponding value. And we can see that both eigenvalues are negative. So this is a sink. So for number 5, our examples so far to indicate that the solution to a nonlinear system always behave very much like the corresponding linear system as long as they near the same equilibrium point. So for part A, we're going to plot this into p-plane, and we're going to see that it's going to behave circular. So, oops, where is my p-plane go? Oh, here it is. Okay. So for this question, very first part A, we're gonna plot, this time go back to X and Y. We're plotting in negative Y, oops, and Y prime equal to X. Keep the same window, and you can see that we plot and it's gonna be circle. And we need to prove it. So we have x squared plus y squared, everything prime, we're gonna equal to 2x and x prime plus 2y prime. And if that's true, we'll just do some substitution. You will get 0, which just this will tell us that why they are circles. So for part B, again, use p-plane to plot some orbit to the system C over the interval -2 to 2, and it's gonna seem like it's spiral towards the origin, but with the blank spot near the origin. So I'm gonna plot x prime is equal to negative y minus 30x to the fourth, and y prime equal to x. And we're doing -1 to no, our window is -2 to 2, and -2 to 2. Okay, let me check that one more time. That's not what you're supposed to get, is that? Okay, in my key, I think it looks like a 3 to me. There we go. Okay, sorry. So it's x prime equal to negative y minus 30x cubed. So you can see that even though it's spiral, but at 0, 0, it still have a blank spot. So for part C, change a small window scale. So we're gonna change this into a really small scale. And near the origin of the orbit should appear to be a loop. Actually, this is not what R is happening. And we're going to use C to prove that if S of t and Y of t are solution to C, then this is true. And our C is 30. So we're going to zoom in. So we're going to go to edit, zoom in, selected rectangle. So remember, hold down the shift key. We're just gonna keep zooming in so you can see that the more you click, it's just gonna be a loop in the middle. And then here is the proof. So we have the equation, and then you do substitution and simplification. We can quickly find out that the left is equal to the right. So that's why it's yeah, the left and the right are equal. So this proves the statement the orbit should constantly move towards the origin because the quantity -60x to the fourth is negative or 0 for our x's. Since x squared plus y squared is the distance from the orbit to the origin, this quantity is decreasing in the orbit while spiral in, and the difference is due to numerical error. So for part D, from the equation triple slot and C, you prove that every nonlinear orbit move constantly towards the origin. However, their graphs in p-plane seems to indicate it's not approach origin at all. So we're gonna use p-plane to plot a specific origin, or sorry, orbit start at x equal to 0 and y is -2, and we're gonna zoom in and see what's happening. So we're gonna keep the same equation. So we're going to zoom like from 0 to like pretty much on the right side. So edit, zoom in. So we're gonna zoom in like right here and see what's happening. So you can see that it's kind of like an arch-ish. So from, it's really hard to like find the radius, but if you like zoom in enough, the radius is about 0.0077 units. And yeah, that is the last part of the lab. So it was a pleasure to have you guys in my lab. I know this is my first time TN, and so not everything is smooth and perfect, but thank you so much for being patient. And yeah, have a great, have a good the rest of the semester, and happy holiday.